Right, so recall. In the homework 6, we were given the function f of xy, which is defined as 4 minus x squared minus 2y squared. We computed that f of x at 1, y is -2. F of y, the partial we show you y at 1, y is -4. And yeah, let's get that picture. So basically, we are given two tangent lines and we want to get the tangent plane that's containing these two tangent lines. That's right here. Okay. So well actually we don't really need the part on the right, so we just need this part. So the method that we know by now is that we can give the directions along these two lines like this, right? So yeah, we also have the equation of the tangent lines. So for this one, let's say this is what this is. We are on the plane y equal to 1. We have z equals to z minus 1 equals to -2 x minus 1. Okay, what's -2? -2 is the incidence rate of change for the tangent line, right? The slope. And here, this is a different on the different plane. This is x equals 1. Then we have z minus 1 equals to the slope is -4 in front of y minus 1. Right? So we know the equations of these two red lines. We want to get the plane out of it. Okay? And what do we do? So we can get the two directions along the lines as vectors, right? And then we want to compute a null vector out of these two vectors. Let's say n, which equals, so this is v1, this is v2. Okay. We just need to get v1 cross v2. So that will be a null vector that's perpendicular to it. Okay. But this is the standard approach that we have done in the homework. Okay. So the question, let's put that down. Let's put it down again. What is the plane that contains the two tangent lines? So we actually know that that the point of intersection, right here is 1, 1. We know how to get the vectors v1, v2. We just need to pick some other points, right? Another point that will help you get the direction, right? And then you do the cross, okay? So this is a standard method. Standard method. Right, now let's get an unconventional solution. Okay, we have two more minutes. So yeah, let's just go and see how much we can cover. So here I like to quickly mention that the quiz next week will cover the section about the gradients, and also we want to cover the tangent plane equation. Okay, so let's see how much we can get. If we cannot finish, then we just continue on Monday. So in unconventional solution. So the previous way is that we calculate the null vector and then we write down the equation of the plane, right? Here we do something different. We know that the plane can be represented, or here we say described by the scalar equation. Which is a times x minus x0 plus b times y minus y0 plus c times z minus z0, which equals to 0. Okay. And here we know we can write it as a function. Okay. So basically here we can put xy portion in the right hand side. So we formulate the above as, so if we do that, we'll have what? We have c z minus z0 equals to negative a x minus x0 minus b y minus y0. Okay. We were looking for the plane equation. Okay. So basically, the first method that we have done in homework is that we're given the lines, and then we're looking for the plane that containing these two lines by finding the lower vector of that plane that we want. Okay. However, here we want to do something else. So basically, we know that the plane has to be of this form. Okay, if we specify that x0, y0, z0. Okay. But then, okay, so here the method is a bit different in the sense that this is the equation of the plane that we want. And then if you intersect with the plane x equals 1, well, that will lead will lead you to one of the tangent lines, like right here. Okay, so x is 1 is the line right here. Okay. And then somehow we are trying to match with the line equations that we are given. Okay. So still need to find A, B, and C. Okay. So in this plane equation, if we set y equals 1, the plane equation, we have what? We have the second term of y is gone. Okay, so the y is 1, this is gone, but you want to also put that y equals 1 as a condition in your system of equations. So this becomes c z minus 1 equals negative a x minus 1. Okay, so when you intersect this plane that you have at the top with the plane y equals 1, then y is gone, right? Okay, so you actually have a function in terms of x and z. Right, and also it looks like a linear expression, right? Mm. And similarly, so I'm going to copy this. Since I do have an iPad, so now you can do the same thing for setting x equals 1. Right. When x equals 1, then the term about negative a x minus 1 is gone. Then you will have negative cat b times y minus 1 is still there. You are setting x equals 1. Right. So now, so when you say x equals 1, that will give you another red line, right? So somehow you are trying to match these two line equations with the equations that we start with. Okay. So recall, so I'm going to cheat again by referring to one of the statements that we have on top. So these are the two lines that we are given. Okay. So recall that our plane contains the following lines that are copied from a little earlier. And also we can compare with the things that we want. Okay, so here compare with the top two systems. And if you think about it, they're really similar. In the sense that, okay, we have the top system is y equals 1 in the second equation, and in the first we have what? We have c z minus 1 equals to negative a x minus 1. And just compare with the second system equation right here, that we have c z minus 1 equals to negative b. Right, y minus 1, right? So you can speculate that, okay, we can just choose c to be 1 and a to be that 2, b equals to be 4, right? Just matching with the existing values in this in these known information already, right? We have c equals 1, a equals to 2, b equals to 4. Okay? So basically, this type of values would work, right? So if you choose c to be 1, a to be 2, and b to be 4, that's a plane will be the plane that contains these two tangent lines. Right, and of course, if you just give like a scalar multiplication of these three values, that's also fine, because if you have like 2, 4, 8, then on this equation right here, you can just try to divide both the right hand side and right hand side by 2, and that's gonna give you the same thing, right? So you see, the choice is not really unique, but if you fix c to be 1, then a and b are determined. So now we know a, b, c values, then we know the plane. Thus, the equation of our plane is exactly z. So you choose c, have c to be 1. Z minus 1 equals to negative 2, x minus 1 minus 4, y minus 1. Okay, so this is just the plane that we want by just putting the values c, a, b into the equation. But we also need to realize, so this is actually z minus 1 on the left hand side, where you put these two expressions on the right hand side, right? You just put them together in your equation that you want, and then that gives you the plane. So now we recall that negative 2 in the Browning's world is the partial derivative with respect to x at the point, right? You also recall that negative 4 there is what is f sub y at the point 1, 1. So the circle expressions, they are linear, they're linear approximations of the function that's intersected with the plane, right? So basically, for the intersections, those are if you think about, let's just quickly look at the figures. If you think about those intersection curves, right? Those are the purple curves. So the tangent lines are linear approximations of these purple curves. So this one, this line is the linear approximation of this quadratic, right? This line is the linear approximation of this quadratic, right? So now we just in the plane equation, we just put these two linear approximations together. That will give you that plane, which is tangent to the black surface. Okay. So that's exactly what happens. Okay. So here, let me put things down. remark. We have computed the equation of a special plane called the tangent plane. Specifically, for the surface z equals to f of xy as the point x0, y0, z0, where of course the z0 is just the functional value of f at the point. Then the tangent plane so basically, if you follow the process that we have done above, then you know actually this part represents the tangent line, where the -2 is just from the partial derivative with respect to x at the point, right? And then if you take these two parts, so that -4 is the partial derivative with respect to y at the point. So you just put the things together. That's actually really simple. So it's just this is the same thing. For the left hand side is z minus z0. For the right hand side, you just put the linear approximations according to what you have on the top. So on the top equation right here in the screen, so this is f of x of x0, y0, which is the partial derivative along the x direction, and then you multiply by x minus x0 plus x of y of x0, y0. So this is the partial derivative of y, you multiply by y minus y0. And here, once again, we specify that z0 is actually the output of the function. And this is the equation for and another remark. The above, well, as we somehow summarize that the linear expressions or the tangent expressions on the right hand side. Okay, we combine two pieces of information together. So this is sort of a generalization of the tangent line concept. Okay, so the above plane is the analogy of tangent line of a curve. Okay, so recall that on the curve y equals f of x in R2, the tangent line at a point x0, y0 is y minus y0 equals to x minus x0, where in the front of the bracket you want to multiply by the slope of the tangent, right? Which is the derivative at prime at the point. And you see how they are similar, right? This y0 is exactly the output at the point. So you can see from in the univariate case, there's only one derivative. But here in the multivariate case, you have two partial derivatives and you put the things together, right? So the only difference here is that there are two terms. Okay, and two variables for tangent. And we do know that the tangent line is the linear approximation of your function f of x, right? So, and this is also the case for the multivariate case. So, let's recall. Linear approximation. So basically the linear approximation is the linear function that you use to approximate a univariate function, right? So a linear approximation of y equals f of x at x equals a is we call it cap L. So f of x approximately equals to cap L of x, where this is defined as the tangent line. So basically it's f of a, which is the output of the function that we start with in the equation right above, plus f prime of a, the slope of tangent, multiplied by x minus a. So if you want to think about the graphical interpretation, essentially, let's say this is the functional graph. Okay, so we have x, y axes. This is y equals f of x. And why don't we move this down a little bit? And then, okay, let's talk about, so if you think about the point, like here is your a, f of a. So this is the x value for of a for a, right? And then basically the tangent line is what is actually the line that's going along the direction of the curve and go through the point in solid. Okay, so this is the tangent line, right? So this is y minus f of a equals to f prime of a times f minus a. Okay, so this is the point slope form, but if you want to write it in the linear approximation form, this is exactly plussing both sides by f of a. So f of a plus f prime of a times x. Tangent line. So basically, the tangent line just follows along the direction of the function at the point in that. Right. And now you can see that possibly the tangent line is not really exact, except at the data point A right here. Right? So when we have a deviation in terms of the input, let's say the value is delta x, right? So your true value of the input is x, which is a little bit far away from the a value. Then essentially, the linear approximation is, so we just draw the vertical line above. Here, the red point is the approximated value, right? Which is x f of a plus f prime of a times x minus a. So basically, the output is exactly the linear expression that we have for the plane, right? But then the true output is on the curve, which is x f of x, right? So indeed, there's a gap. Okay, let's still put it in black. So there's a gap of the output value, which is the approximation error. So basically now we can think about a few concepts. So first one is the term called differential. So differential is actually the way that you approximate the change in output by in terms of the change in input. So it's dy equals to f prime of x dx, right? So when you think about the differential, this is exactly saying, okay, the change in y must equal to the slope of tangent times the change in x, where dy dx represents the change in the output and the input. But then they are denoted as d because you are essentially lying on the tangent. Okay. So differential always directly relates to the tangent. But then when you talk about the differentiable function, at x equals a, it's a little bit different. So basically, when you talk about the differential function, it's about the limit, right? So it's the slope of the secant, and you change you change delta x right here. So delta x is a change in the input. If you push delta x to 0, then the slope of the secant will approach some some value, which is slope of tangent, right? But basically, if we want to write it in terms of the functional values, it's something like this. It's delta y equals to f prime of a times delta x plus this is an expression that's out of the which represents the gap, right? Because this is the change in y. That's actually from this first black point to the second black point. Okay. If we want to draw this out in the figure, I'm gonna get the dashed lines right here. So the change in y value, delta y, is exactly. So I'm just gonna quickly highlight. So this is the change in y, right? This part is the change in y for the tangent line. Okay. So delta y is the larger, well, in the picture, is the larger purple bracket value. And here, this is the smaller bracket value, which is from the original black point to the red point. Okay. So there's a gap, right? The gap is represented by delta times delta x right here. Epsilon delta x. And this epsilon represents what? Represents the gap over the changing x. And this epsilon goes to 0 as delta x goes to 0. Okay. So this way of writing the differentiability is a little bit different in the sense that we used to write it in terms of the slope of tangent. Okay. And here that actually represents f prime minus f of x minus f of a over x equals a. Okay. So that's what it represents. And usually it just approaches 0 when your x value approaches the a value, but not exactly a. So let me just put it here. Right. So well, we don't really have to be super formal because if we just think about a few pictures, you will get the idea. Right. So when we talk about the slope of the secant approaching the tangent, actually what it says is the following. So basically, there is indeed a gap, right? So from the true function value to the linear approximation, so there's a gap, and then you divide by the run. It should be a ratio, but then the ratio should get less and less. So the difference between the slope of the tangent and the slopes of the secants are just getting less. So I'm just doing the illustration for the slopes, but I don't really want to keep it in the figure. But the point here is that the purple gap over, you somehow have to think about the ratio. So here indeed, the gap is getting smaller when you approach that red point, but I want to claim that the ratios are getting less and less, approaching zero. And you can see that from the slope. From the slope difference. Here is on the left hand side the same thing. So the slope is like this, but then it's getting closer and closer to the slope of this tangent line at the point. Okay. So this is the kind of function that is differentiable. What happens if it's not differentiable? So if you think about a function that has a sharp corner, then it will not really be good. So think about the kind of absolute value of this kind of function. Okay. So if you have a sharp corner, you know in Calc 1 that this is not differentiable, right? But then what happens here is that if you just draw a linear approximation like this, then the gap over the run in terms of x is always a constant, right? Because on the right hand side, the slope of secants are always this direction, okay? And the slope here is never agreeing with this red tangent line in a sense. Okay. On the left hand side is the same thing. Okay. So the gap here is even larger, and then over the changing x, the ratio is always the same constant. So they have to approach zero on both sides in order for the function to be differentiable, which is not the case in this figure. So differentiable, not differentiable. So you can see that for differentiability, well, the algebraic way is always a definition that's somehow easier to understand than the geometric perspective. Well, especially in terms of that ratio of epsilon right here, it's not really straightforward. So so this is the thing that we only want to discuss in Calc 1, but probably in multivariate calculus, we just stop at the concept of linear approximation. So let's just quickly generalize what we have seen. So linear approximation is we just use a linear function to approximate a multivariate function. So the only difference here is that instead of the tangent line in red, we're now using a tangent plane. Okay, so this is f of xy. We are approximating using so this is the same name, capital L, which is a linear function, and we just express the linear function using the tangent plane we have introduced. Okay, so this is f of x, f of ab. The function value plus now we have the differential. So basically it's f sub x of ab times x minus a plus f of f sub y of ab, the partial with y, multiplying by the changing y. Y minus. Okay, so it's just a linear function on the right hand side. So similar definition for differential and differentiable functions, differentiability. Well, we certainly would not elaborate on this concept, but the differential is exactly this part, okay? We will put it down at the end, but here, the emphasis is the linear approximation function. Okay. So example. Let's say we look at the function z equals to 2x squared plus y squared. At the point x equals 1, y equals 1. So we can write down the tangent plane. At 1, 1. So here, we just realize that the output z0 at the point x0, y0 is what? Is 3, right? So you plug in 1, 1, that will give you a 3. So z minus 3 equals to. So here the x, so the partial derivative in terms of x for the function is 4x. So now that's going to be a 4 at 1 times x minus 1 plus. Now the partial with respect to y is 2y, so it's going to be a 2 times y minus 1. Okay. So the tangent plane also represents the linear approximation. Here you just need to plus 3 on both sides. That will give you the linear approximation. Okay. So now we consider the function, the value for the function at a point that's slightly deviated from 1, 1. Okay. So here we put 1.1, 0.95. Okay. So basically here this x value is increased by 0.1 and the y value is decreased by 0.05. Right. So in this situation, the linear approximation is Capel of 1.1, 0.95. So we just write it down as the linear approximation. So basically, at 1, 1, the function output is 3. Now we plus, okay, so 4 times, now the x value is 1.1 minus 1. So basically, it's just 0.1 units away from the original input, right? And plus, now 2, we have the original, we have the current input to be 0.95. It deviated from 1 by a really small amount. Okay, we just now just calculate. So this is 3 plus 0.4 minus 0.1. Just do the input differences and then multiply by the partial derivatives. Right? And essentially, we see that the output, if we were approximating using a linear function, then the output is like 0.3 units away from the original output. Okay. And now this is actually an approximation that's not so bad because the true value, if you plug in 1.1 and 0.95 in the original function, it's pretty close to this value. Is 3.3225. So the error here is going to be this part, which is not really big. And the thing, and if you just imagine that for your curve like this, for your for your two-dimensional x well for your surface in 3D, if you are just doing the approximation in terms of the tangent plane, then the closer you get to the xy pair, then the better the approximation is. Right? So this is the expected. So as a remark, linear approximation FL for function f follows exactly the equation of the tangent line. Since z equals to z0 plus f sub x at the point times x0 minus x0 plus f sub y at the point times y minus y0. This is exactly the tangent main equation where you just move the z0 on the right hand side. Since this equation is the equation of the tangent line. Indeed, we can also observe that since the function value is approximately well, the linear function value, linear approximation value, the change in the output z, which is f of xy, the latter output minus the prior, this is approximately f sub x at the point times delta x plus f sub y at the point times delta y. Here, delta x is exactly x minus x0. So it's the same kind of notation if you are thinking about the exact change in the inputs. Okay. So basically, when you think about the exact change in input is delta x, delta y, and then the true output change is delta z, right? So this right hand side, this is the differential. If you switch to dx dy notation. But then what we express here is that the exact change in the output is approximately the differential that you write at the point. And the differential once again relates to the linear approximation. So this is approximately equal, but it's not the exact. The above is an approximation of delta z using linear approximation. So here, just note, we define differential to be dz equals to f sub x at the point dx plus f sub y at the point dy. The differential, whenever they talk about this term, it just means that you are using the tangent plane to do the approximation and represent the change. So that's pretty much all we need to know about the tangent planes and the differentials and the linear approximations. So, so this is the well, the last topic that we cover for the quiz tomorrow. Basically, so there will be 3 questions tomorrow. One about the directional derivative, one about the meaning of the gradient, which is the direction along which your function increases fastest, right? And also, and finally, there's a 3rd question about the tangent plane. So the computation of the questions may not be really complicated, but you need to understand all these concepts. But the tangent plane is still, I would say, relatively intuitive. So this is exactly one application of the partial derivatives, right? It's actually a really straightforward one. So basically, the linear approximation, you just put the functional output here, and then the partial derivatives here, right? So that can give you the tangent plane equation. So that's actually pretty straightforward. And now, in the coming section, we are gonna do more complications of partial derivatives.